Okay, good. So I guess maybe let's get started. So
Okay.
my pleasure to introduce the next speaker, Antonio Gonzalez-Arroyo from UAM in Madrid, Spain. And he'll be talking about fractional instantons and their dynamical role. So please, Antonio.
Thanks very much. Well, I want to thank, of course, Sayantan and the rest of organizers for inviting me to this very interesting workshop. Of course, I'm going to talk about something that I've been working for a long time, I mean, over 30 years or so on, and I've written many papers. And I find with great pleasure that some young generation of scientists are getting interested in this. And some of these people are present in this workshop, like Mithat or Sayantan or Larsen and so on. So let me share with you. So let me go back to where I was here. So I want to say, first of all, what fractional instanton is, because there is a lot of confusion with names. I will talk a little bit about names in the first few slides. The first thing about fractional instanton is, for me, it's a self-dual configuration of four-dimensional Euclidean Yang-Mills theory, which has non-integer topological charge. Furthermore, by being self, let me also fix some names which will be a little bit different from the names that other people are using, but just to make sure that we understand each other, what I would call...
Can you go to full screen mode?
Okay, sorry. Okay, so what I was saying is that I use names which are associated with the physical interpretation of these singular topological objects, which are related to codimension. So essentially, anything that has a codimension 1, I will call it domain wall, codimension 2 vortex, codimension 3 monopole, and codimension 4 instanton, because this is, of course, in conflicts with the use of instanton that Mithat was using the other day for objects that were not in 4 dimensions, okay? So I continue and just want to state some very basic questions that a mathematician would like to ask when you hear about topology in the context that we're using it. Of course, we know the answer to these questions, but nevertheless, for the sake of the students, and let me just pose it. One of them is what happens with topology when the base manifold is non-compact, when it's R4, for example, because, I mean, from the mathematical point of view, if the base space is non-trivial, there is no topology, okay? The second thing related to the previous one is how can topological objects affect the dynamics in this case, that the space that we are dealing with is infinite, is non-compact like Rn. And finally, how can topology play a role in the case of quantum fields? Because, I mean, topology relies on continuity, and quantum fields are very rough things. Actually, they are distributions beyond two dimensions. They are not supported on continuum functions. So that's just the guidelines so that we can ask these questions as we go on. And I will start first with the very most simple example of where you get topology to work, which is the case of one-dimensional field theory with a scalar field having this energy density, which has a kinetic term and a potential term, and the potential term is given by this double well potential. It's easy to see that the solutions that have minimal energy are just constant phi, either 1 or -1. However, you can find other solutions by doing the following. I mean, this, of course, is like T minus V if the change is sign. So we know that the corresponding Euler-Lagrange equations conserve energy. So you have to just to think of this as minus V to realize that this thing here, which I call fake energy, is conserved. So by just taking this fixed value, you can get solutions. And the advantage is this equation is just first order, not second order, like the ones you get from the Euler-Lagrange by minimizing this. And if you do that and you put anti-periodic boundary conditions, you get this solution, which is simple, which is called the kink, and which goes from -1 to +1 at infinity. And here I drew the kink solution together with the energy, which goes from 0 to 0 and has just a local position, okay? Now, let me fix a bunch of interesting things about this configuration, because I will contrast it with the ones we will find later. First, because it's having to do with topology, you can see this as topology because you can think of this gauge field as a vector bundle, Z2 vector bundle. And if you try to put this vector bundle in a non-trivial setting, like a Moebius strip, then you get automatically these solutions. So we see, sort of in answering the question that I was asking before, that what happens when you take this Moebius strip to infinity is just that you get R, and then it's just the condition that I put before, antiperiodic boundary conditions, okay? The second thing we see from this equation is that it has a free parameter, which is the center of the kink, which is where the field vanishes, The third thing is that it is exponentially localized in X, because the Lagrangian, the energy, has a scale parameter, which is this square root of lambda. So that's how these things enter. If you take this square root of lambda to infinity, you get the Ising model. So that's a limit of infinitely massive case. Now, what happens when you hit this system? When you hit the system, you start producing groups of kinks and anti-kinks that have to continue this way, like this, plus fluctuations, which are not put in here. And the energy of one of these configurations will be the sum of the number of the energy of each kink times n, plus some interaction energy that, for example, Mittag was talking about the other day. But I am interested in the dynamical role. And the dynamical role is huge because you can compute the correlation between phi at two different points and deduce that it decays exponentially. And that forces the expectation value of phi to be 0. So there is no spontaneous breaking. But this can be seen as a consequence of the existence of the kink, because this P here can be related to the probability of creating a kink per unit length, okay? Now, so if we go to higher dimension, these kinks, which are domain walls, will become, they have to be continuous. So they develop into Peyer's contours. That would be sort of the Ising picture. But if you have considered the previous one, there would be some kind of thick walls. And but the important thing here is that because the energy is linear with the length of these contours, the entropy is also linear. But the energy is damped with the with the temperature. So at low temperatures, as we all know, the expectation value of phi would be different from 0, and you get a magnetization that happens in the Ising model in 2 dimensions and also in the lambda phi 4. Okay, so we go to the next model where we want to learn a little bit about these kind of things. Most of you know all that, but anyway. The second example is the Abelian Higgs model in 2 dimensions. Here, what we have is the electromagnetic field together with a scalar field, which is complex and charged, coupled to the electromagnetic field. And I put a potential here, which is the Mexican hat potential, which also has a circle of minima. This is actually a model, an effective model of a superconductor. Well, if we ask the same questions, what is the minimum energy configuration? You immediately realize that the minimum energy configuration is the one that has 0 magnetic field, and the phi, the charged particle, is constant, equal to e to the I alpha, because I forced the modulus to be 1, okay? Now, we go to topology. In this case, we are dealing with gauge theories. In the case of gauge theories have a geometrical interpretation as vector bundles, in the case of the matter fields, coupled to a connection, and the connection is the electromagnetic field. So the electromagnetic field can be seen as a connection in a vector bundle. This Higgs field is just a section of this bundle. And if we can ask the mathematicians or look what is the topology of these structures, you find that there is so-called Chen classes, which are elements of the cohomology group, or even values of the cohomology. So it's 2 forms, 4 forms, 6 forms, and so on and so forth. In this particular case, since we are in 2 dimensions, there's only the 2 form, which is just actually the magnetic field. And what the mathematicians tell us is that this number, which is this quantity, which is called the Chern class, when you integrate it over full space, it gives you a number which is quantized. Actually, you get 2 pi over n, and this has an easy interpretation. That's the magnetic flux, which is quantized. Okay, so let's look at the solution. If we frustrate the minimum action solution, if we take n equal 1, then we're forcing flux into the system. And then we frustrate the solution that we had before. And what we are producing, if n is equal 1, is what is called the Abrikosov-Nielsen-Olesen vortex. I have here a picture and also the contour of this Abrikosov-Nielsen-Olesen vortex, where the energy is centered at one particular place and goes down to 0 at infinity. Now, let me see what properties this ANO vortex has. The first is that the magnetic field peaks at the center at x equal x naught and goes exponentially to 0 as you move away, okay? And the Higgs field vanishes at the center, so the position of the vortex can be identified with the 0 of the Higgs field, and goes also exponentially down, well, sorry, up to a modulus of phi equal to 1, okay? Now, there are two scales in the problem, but if the two scales become equal, then you get what would be sort of critical superconductor. And in this case, the equations become simpler. Like in the previous case, we get equations which are first order rather than second order. They are called Bogomolny equations. And in this case, we can find the solution of these Bogomolny equations. And like in the previous case, there is they satisfy the Bogomolny bound, which implies that you can compute the action, which is completely determined by the value of the flux, okay? Now, here, the solution is unique modulo translation. So in this case, the space of solution is just translating. So it depends on two real numbers. X naught is a 2 vector. The shape of the solution is not expressible in this case in terms of an elementary function like we did before with tangent hyperbolic. And there is something very peculiar that I have used to try to handle these guys, is the fact that a mathematician discovered that this is a pretty general phenomenon, by the way, is that there is a particular value of the area, which is 4 pi, in which there is a very simple solution, a solution in which the magnetic field is a constant and phi is 0. That is called the Bradlow limit, okay? But here we have a solution. So what I did with a student a bunch of years ago was to try to construct an expansion in this deformation of the area from this critical area to find a solution at arbitrary areas. And actually this plot here, this figure, is precisely the result we got, okay, of this effort. Let me go on and tell you why it could be useful when we go to multi-vortices, which in this case, they are solutions, of course, with n bigger than 1, okay? What do we know about that? We know that first, as I told you before, the energy is exactly additive, so there is no interaction energy, but the problem is highly non-linear, so it's just a magic that this happens. Second, another thing we know for sure is that the space of solutions is, or the moduli, what we can call the moduli, has 2n degrees of freedom. So, which can be interpreted like the positions of the n different vortices. Okay, so, and the position of the vortex can be identified by the 0 of the Higgs field. You can prove that there is as many solutions as zeros of the Higgs field. And there are, of course, 2 coordinates for each center, for each of the zeros. Of course, it can happen that 2 of them coincide, yes, but that would be a submanifold of lower dimension. So if you just do randomly, taking into account that they all have the same energy, that will just an exception that will never happen. It's entropically suppressed, okay? Now, applying the method I was mentioning before, I can derive analytic solutions given the position of the zeros in advance. So that's very good because you can, of course, try things that are much harder to obtain by any other numerical method, because I can fix that and I compute you have an analytical tool. So you have an expression in powers, of course, of this deformation. And you can do things like, as we did, scattering. You can just take two, give them some energy, some kinetic energy, and see how they scatter and relate, for example, the angle of scattering with the impact parameter and things like that. You can do that analytically, okay? The same thing I did with another student was to compute, for example, the quantum contribution to the mass of this thing, okay? Let's move to Yang-Mills theory. Okay, now we have to switch to 4 dimensions, and we have to replace these energies by the action, Euclidean action, okay? There you have the expression given both in terms of the trace in the fundamental representation as well. You can, of course, use just the generators. Ask the same question as before. What is the minimum action configuration? The answer is easy. It's a pure gauge, which is of this form, and F mu nu will become 0, okay? Now, again, we get into topology. If we are thinking of SUN Yang-Mills fields, we can see that the first Chern class that we used before to classify the topology of this two-dimensional Abelian Higgs model is not existing in this case. It's always trivial, it's 0, okay? So, but we're in 4 dimensions, so we have the second Chern class, which is a 4 form. And by integrating this 4 form over the manifold, whatever it is, we get a conserved quantity which characterizes, which is actually in the situation typically an integer, which is characterizes the different sectors which are topologically inequivalent. That's called the topological charge of the instanton number. So if we play the same game, that's actually what Belavin, Polyakov, Sparks, and Tupkin did many years ago. You can just try to find what is the action, the configuration that minimizes the action in the presence of a non-trivial, non-zero value of the topological charge. And you get the so-called BPST instanton, whose form is also quite easy, analytic, given by these rational functions. So both A and F are simple. They're just polynomials, actually rational functions. So let me look, as I did before, to look at the properties that this solution has. Some are similar and some are different to the ones we found before. First of all, the action density peaks at the center. So we also have translation invariance, and therefore we have as many solutions as the center, and the action density peaks there. However, the difference is that there is no length scale in the action of the 4-dimensional Yang-Mills. Therefore, it does not decrease exponentially away from, as we can see. It goes like 1 over, the F mu nu goes like 1 over x to the power 4, okay, as you move away from the center, okay? Furthermore, because there is no size, this size appears as a new parameter in the game. So this is a new parameter which characterizes the solution, which is the overall size, as specified by this value rho here. Okay, and another property which also goes in the line of what we said before is that this solution is actually a self-dual solution, therefore, which it is the solution of a first-order equation rather than the second-order equation, and in the same way as before, the action is fixed by the topological charge through the Bogomolny bounds. What happens with multi-instantons? We are just playing the same game in different theories, okay? Now, here, even if the gas is dilute, where you can see these lumps of energy which are here and there, you should not add the fields. I say this because some people do it. You cannot produce new fields you cannot make the Q equal 2 by adding the field of Q equal 1 at different points. That would be a mess. It doesn't have the properties. You just check, it doesn't have the topological charge, it doesn't have the action that you wanted, okay? But that happened for Higgs and vortices. for vortices, you cannot add the field because the field goes to 1. At infinity, if you add 2 fields, you get 2. In the same thing with Higgs. So it's not completely strange that this also happens here. It's a very nonlinear problem. Okay. Nevertheless, Toft found a method to sum. But of course, it involves a logarithm, as you can see in this formula here. This is called Toft ansatz. And in this case, you can produce multi-instantons by an additive process in which you just add here in this function a collection of fractions involving sizes and positions. Rho and xi are just free parameters. And for any of those, you can sum over many, and you produce multi-instanton solutions with as many topological charge is equal to the sum, the number of these terms here. In particular, if you take only one term, okay, you get, of course, the same instanton that you wrote before, but in a different gauge. You will not get the same number as before. It doesn't reproduce the A mu you have here. You see here you have eta bar instead of eta. This is in the singular gauge. In this gauge, things decrease much faster, and it's better to, if you add, do it in this gauge, not in the other gauge. That's very important, okay? So, but if you compute, of course, gauge invariant things, it will be the same thing. But for the field itself, which is not gauge invariant, is not going to be the same. This form, you can do the derivatives and find it by yourself. Okay. Now, this is nice because I have a way to construct new instantons, multi-instantons, adding inside the log, but you can do that, okay? What happens if you apply this? First thing you can do is you can play the game by well, I can construct instanton on the torus by just taking an infinite number of instantons equally spaced in one direction with the same row. And then there is a period, which is just the distance between the two, the one instanton and the next. And you can play this game, okay? You can do it. And the answer is you get something reasonable. And this reasonable thing actually turns out to be the so-called Sherrington-Kilpatrick caloran. So it gives a right thing. However, if you want to do this in two directions, it will blow up. As you can see easily, because it's the sum, double sum in two directions of 1 over x squared. As you can see there, the position here comes square, and you have a sum, which is a double sum. It will be a logarithmic divergence, okay? This is important because it's a consequence of the fact that the field does not fall so fast in this case because there is no scale. Okay. Actually, it also happens in ordinary electromagnetism if you take an array of charges, all the same sign, because the field decreases with Coulomb law, and if you add the field, it diverges. You cannot put an array, a two-dimensional array. You can put a one-dimensional, not a two-dimensional. Actually, that's a physical interpretation for something that has been proven mathematically. You cannot put one instanton on the torus. Okay. This does not happen for vortices because they are exponentially localized. So the field dies away very quickly, and it's not the case in this particular instance. Okay. Furthermore, this ansatz that Toft found is not the full story. You can see that it doesn't give all the solutions because actually you can count the parameters, and as you see, for every value of the Q, you have a size and a position, which is a 4-dimensional location. So it's 5 parameters per Q. And if you add, that's 5Q, okay? And it can be proven on the basis of the index theorem that actually the number is much larger. It actually goes like 4QN, okay? So that's created a kind of struggle or kind of competition between mathematicians and physicists to try to find the full set of solutions. Finally, this set of mathematicians, Atiyah, Drinfeld, Hitchin, Manning, arrived to what is called the Adhm construction, which is a way in which they can generate, they can construct solutions which having the right number of parameters at any given Q. Nevertheless, there is no generic arbitrary solution that you can give. I mean, you can do it for Q equal 1, 2, 3, 4, 5, and so on, but you cannot give the solution, unfortunately. Yeah.
I have a question.
Yes, go ahead.
I do not understand your remark saying that one cannot construct a 2D array and your remark on electric charges. If I have an array of electric charges and, you know, two-dimensional lattice of electric charges, and if I go away from this, you know, this two-dimensional lattice just by a little bit, it will just look like a plane with uniform charge density. That's it. An electric field will be pointing.
Well,
in the upper part, it will point down in the lower parts. I don't see any obstruction there.
I mean, I'm just adding the fields, and of course, it's 2 dimensions. Maybe that's it. Okay.
I personally do not see any obstruction there.
Okay. But it's a fact that you cannot construct in this way. I mean, you can do the exercise and see diverges. Okay.
Yeah. No. So in the case of electric field, for example, you say the same problem for electric charges. Of course, the potential diverges, but if you look to the electric field, more precisely, potential is a divergent part, and it is a part which is proportional to the absolute value of distance from the plane. And that's the physical part. If you take derivative of the potential.
Okay, sure. I diverge on the plane, not away from the,
But you are looking to the field away from the plane when you put this two-dimensional array.
Yeah. Okay. Well, let's stop that. I mean, okay. I think I'm right, but anyway, let's discuss that later. Okay.
No. I can't prove that you are not right.
Okay. Good. let's go on. Okay. So the main thing here, okay, is that the number of parameters, as you can prove, that goes like 4qn, actually with a subtraction because it's not exactly this number. It depends on the manifold in which you're writing it, and actually you can ask the question of what was missing in the construction of Toft, and actually what was missing was the orientation in space in color space of these instantons. So what the Toft construction gives you is just a collection of instantons which are all pointing in the same direction in color space. And that's what diverges, okay? Fine. Okay, so now let's go on to the next question, which has to do with twist, actually. Now, Toft realized that since the theory, if you consider just Yang-Mills theory, you have actually the gauge group is not really SUN, but SUN over CN or PSUN, as Smith was mentioning the other day. And in this case, there are also new classification, new classes, characteristic classes, which are called Stiefel-Whitney classes, which classify different bundles, okay? And in the literature of physics, this was introduced by Toft under the name twist. And you can see it very easily as if you start with UN, and then you project down to SUN. Because normally what happens is that this, when the UN field had a first-chain class, non-trivial first-chain class, it will build into a twist in the SUN projection. Okay, so it has to do with that. The difference is that now this flux is now quantized modulo n. So that's the difference in the case of the ordinary first-chain class. The flux is an integer through any of the planes. So in this case, it's just modulo n. Okay. Now, one thing that you can also find out easily from that construction is what is the value? How does the topological charge become what is the value of topological charge in this if these sectors are non-zero. Well, here I consider the case of the torus, in which in every plane you have a non-contractible plane, non-contractible surface, okay? So I can define a twist or a first-gen class, if it was, for example, UN, for every plane. So in every plane you have an integer, mu nu, but this time they're defined modulo n, okay? So if in case that this n0i and mi defined in this way here, I mean just the spatial or temporal, the electric or magnetic components, say, of this mu nu are both non-zero, then you can see that the topological charge gets this value, where z is an arbitrary integer. So what you get from here is that this value is not necessarily an integer if this number here is an integer which is not divisible by n. And actually that happens. And there exist these subdual configurations, which are minimum action solutions, when this Q is non-integer, and this is what I call fractional instantons. So the action in this case, because they are also self-dual, is fixed by the topological charge, but this time you get an n in the denominator, okay? Let's see of these building blocks. Let's look at the minimal. Of course, you have Q can be 3 divided by n, but there is a basic building block, which is the configurations that have the minimal possible topological charge, which is non-zero, which is 1 over n. N is the rank of the group, okay? So you can look at what are the solutions, and you can do it, for example, numerically, and you can find solutions which satisfy the self-duality condition, and they are lumpy. This is one of the examples I gave you before. This is if you integrate in 3 directions. If you take a torus which is very large in one direction and short in the other 3, then you get by integrating, you get something which is localized in time. Of course, in space, it looks like this, okay? In time, it looks like this. It goes to 0 at infinity. So in some sense, the limit exists in which you can take this torus and take some directions. In particular, in this case, I took one direction to infinity. And there is a limit, the limit exists, and it gives one of these possible fractional instantons living in TD times 4 minus T minus 4 minus D, okay? R to the power 4 minus D, okay? This you can do by in 1, 2, 3 directions. If you do it in 2 directions, if you take 2 directions much, and you can do it by taking the torus and taking 2 directions to infinity and compared to the others, and see if you get a solution that stays constant, does not converges, even if you take the 2 directions very large, and indeed you get it. And this is one example of what you get. I would call it a vortex because it has the properties that I would define before as a vortex. It's a 4-dimensional object, which is a string in 3 dimensions here. It's a point in 2 dimensions. This is depending on how you cut. You see the 2-dimensional, 3-dimensional, or 4-dimensional, and it's a sheet, which would be just the world line, the world sheet of this vortex. But if you do this with 1 direction small and 3 directions large, you get what you can call calorons, and indeed this can be treated even analytically if Q is equal to 1, and this is the procedure that a few people like Kran and Van Baal and Lee and Lu developed to obtain analytic formulas for these other objects, which they start with Q equal 1, but as you see, this is SU3, they decompose into 3 components. Each one of these is what I call the fractional instanton. Of course, the whole thing has topological charge 1, but each one of these has topological charge 1/3, which corresponds to SU3, okay? Okay, he called them monopoles, and actually it's the name monopoles applies because they're sort of things that are one-dimensional in 4 dimensions, because along the direction S1, they are repeated, like the example I gave you before of the Sherrington-Kirkpatrick caloron, but these are different. Okay, how are these objects connected to each other? Okay, there is one very nice mathematical transformation that was invented actually for monopoles, but that suits perfectly this kind of solutions, this kind of self-dual solutions on the torus, because you can use them to do the following. If you are given an SUN self-dual configuration on with charge Q on the torus, you can construct, actually it involves the Dirac operation, the solving the Dirac equation, a new self-dual configuration, which is living in SUQ and has topological charge N, and it's living in the dual torus. Okay, that's a very nice thing. Unfortunately, that doesn't give you new things like in other solitons, because if you apply it twice, you get back to this one, okay? What I did, that's part of my work, I applied this idea to the case of fractional instantons, and I found that these basic building blocks map onto each other for the same value of N. You can do it, despite their fractional instantons, and despite that this involves the solving the Dirac equation in the fundamental representation, you can do it. And in the end, you get this mapping, in which, of course, if 2 directions are large and 2 directions are small, like in the case of the vortex, they map to each other. I mean, the big ones become small, the small ones become big, and so this structure becomes self-dual. While on the other hand, here, the one which is S1 times R cubed maps onto, the one which is T3 cross R maps onto the one which is S1 times R cubed. And this is actually the calculation that we did in a paper with Pierre van Baal and other people, in which we calculated numerically this guy, analytically this guy, made the NAM transform and matched them, and they match perfectly well, okay? It's a very interesting thing to notice that actually the ADHM construction can be seen as a limiting case of the NAM transform. Okay, now let's go to dynamics. I will talk about confinement. Okay, I'm a little bit behind schedule.
You have about, I would say you had some technical difficulties. You have like 15 minutes or so.
Okay, thank you very much. Okay. Okay, let me say very quickly, well, confinement is a property that was introduced to explain why we cannot liberate quarks. But after a while, it was very easy that it's a natural phase of gauge theory. And it's also clear what you need, that is chromoelectric flux tubes become energetic and with an energy that grows linearly with the length. And as a matter of fact, we know that in superconductors, the magnetic fluxes have this property, as we were mentioning before. So I think it was Parisi that mentioned that if there were monopoles, the monopoles inside a superconductor would be confined because it has the same properties. This generated sort of a kind of picture called this dual superconductor picture, which essentially explains the phenomenon by saying that what we have to do here is to switch from magnetic that you have in superconductors to chromoelectric to get really what you need for the description of confinement, okay? That's overall theory like London theory, which describes things, but we lack a microscopic theory of the type of BCS theory in the case of QCD, despite that we have a lot of evidence that actually the phenomenon takes place. Okay, Ken Wilson introduced the discretization of gauge theory, what are lattice gauge theories, and gave us an operative criterion for confinement in the case of Jamnier's theory, which is simple, which is just that the Wilson loop, the expectation value of Wilson loops, which are given here, should fall like the area. Okay, this has an easy interpretation because this is just to be supposed to be two quarks separated a distance L. and here the same, and this is time, and then the energy is just what you get the exponential of the energy times time, and the energy goes linearly with L. That's what you need, okay? It's easy to construct the theory of gauge theory, a discrete gauge theory that confines. Actually, in 2 dimensions, you construct the theory associated to gauge group Cn, and it confines at temperature 0. Why? Because it's enough to put in here what you call a vortex, something that that introduces flux, that costs a finite amount of energy to automatically disorder the loop. So you can do the calculation. And actually, if it's in this case, the calculation you do is exactly the same one you did before for this domain walls. It's exactly the same formula to prove that actually this theory confines. You can compute the string tension, okay? Okay. However, this mechanism doesn't work in 3 dimensions. Why not? Because as I said before, these vortices in 3 dimensions, they develop into strings. And then these things will have an energy per unit length. And it's the same thing as with Peier's contours, that the energy of this length of this vortex line grows linearly. But it has to be very big, because this is something asymptotic. It has to cut the inside of the Wilson loop and the outside of the Wilson loop. It cannot fall inside the Wilson loop, because that would not give you confinement. So that tells you that these theories do not confine at temperature 0, at very low temperatures, when you go to 3 dimensions, okay? However, in 3 dimensions, if you put in monopoles, then it confines, as it's what was found out by Polyakov and by other people. You can put that, and you see it confines, because in this case, what you create is a pair of monopoles, monopole, antimonopole, and the flux to be between them, and that costs a finite amount of energy, okay? So what happens in 4 dimensions? Well, the problem with monopoles is again happening because monopoles become strings in 4 dimensions. They are just the whorl line of these monopoles, and it has exactly the same problem. They are not, they will give you a divergent energy for these monopoles that are long enough, okay? So you need something else. You need something that that is not a monopole. And actually, if you look at the solution that we found before, you see that what you need is something point-like. Okay, because that was the solution. That was why in 1 dimension you had phi equals 0. In 2 dimensions you had phi equals 0, etc. So the reason why you had that was just that you had an object that had finite energy of the right dimension. So these things depend very strongly on dimension. So you need something point-like. You need something that carries flux, because otherwise it will not change the Wilson loop. Actually, the instanton doesn't work, okay, because it doesn't carry flux. Also, it doesn't have the good Large-hand limit, and we know that in the Large-hand limit we have confinement. And we need something genuinely non-Abelian, because we know that the Abelian theory does not confine at t equals 0 in 4 dimensions. So we have a natural candidate, fractional instantons. So let's try. So what I did sometime in the past was just to create an ensemble of fractional instantons, okay, which is easy because they are all fractional instantons. So just replicating one fractional instanton, you create a gas, then you shake them a little bit to move the positions, because the positions are free parameters, okay? And then you measure the Wilson loop. And that's what I found. I found really that if you take the string tension to be the logarithm of the Wilson loop expectation value divided by the area, you get a constant, which is just the string tension. The different values is because it depends on the densities you put. So there is a correlation between the density and the string tension, okay? Okay. Let me also illustrate a nice exercise that I did a long time ago with some of my students, which is in the same spirit of what Mithat is doing with this adiabatic continuity. It's to consider the size of the system as a parameter which I can tune to move myself from the situation in which semi-classical calculations are valid, they are rapidly convergent, to the situation in which you are with a very large distance and you recover infinite volume space. infinite volume, okay? So the difference is that what we were considering was just a three-dimensional torus times R. So it's on the way of what I was mentioning at the beginning, this candidate that I had here. And the torus has another very nice advantage, is that it can trap chromoelectric flux. Without putting the quarks, you can put in, because you can have a closed line of chromoelectric flux that winds around the direction of the torus. And that makes it that you just have to measure the decay of this as a function. It has to decay with the area of this cylinder, okay, which is the time times the distance, the length of this torus, okay? So you can measure the correlator of an operator which creates this chromoelectric flux as a function of time. And this measures the energy of this chromoelectric flux as a function, which depends, of course, on the size of the torus, which is also the length of the chromoelectric flux, okay? So what do you get? Of course, if you go to very small L, because of asymptotic freedom, you get that you can handle this problem purely with methods which are analytic, which are semi-classical. In particular, some of them can be computed even in perturbation theory, some of these correlators, but there is one very special correlator for one of these loops, which is parallel to the direction of the magnetic field, which I put a magnetic field in this torus, is zero. Has two minima. One with P equal +1 and the other one -1. So it becomes very similar to the one-dimensional example I started with, okay? So, and what do you see? Well, you see these objects which are similar, very similar just to the kinks that I was describing before. This comes from a simulation. This comes from a simulation, and these lines are actually no fits. They're just, once I fix the position, I know the shape, because remember, there's only one object with topological chart 1/2. It only depends on the distance. You can move it, but you cannot deform it. It's not like with normal instantons. Sometimes you get normal instantons, okay? But this is a configuration that you generate, and you can perfectly match. Here, of course, I'm writing the energy, but here I'm writing the field. So you see, this configuration does not flip. It's not antiperiodic. There is no twist in time, and it goes from +1 to +1, okay? And anytime you get a cross, you get a peak here, because they are associated, of course. That's essentially like in the case of the kinks. So it looks very much like kinks, okay? So, and you can even compute this number EL two ways, by measuring and also by computing how many of these guys you have. They are distributed Poisson-like, and you can compare if this semi-classical calculation works. And indeed it does. Indeed it does. Okay, you compute this energy, which depends on the size of the torus. And how does it come out? I mean, this is an interesting thing, because this is the calculation, of course, the probability. This is proportional to the probability to create one of these instantons per unit time. But the probability is done by the action. It's the exponential of the action. So this is what you get here. In this particular case, this is SU2. That's why you have this that with this power here, which is important because it comes from number of zero modes. This is a very similar calculation to what Toff did with the ordinary instanton. What happens is, of course, the renormalization group tells you that despite the fact that these objects apparently do not depend on size, that their energy does not depend on size, because of the renormalization group, this G here actually has to be computed at the scale of these things, which is L. And that predicts that actually this energy will depend on L in a way which is fixed by the coefficients of the beta function, which is, in this case, is 1/3. It's different for an instanton, because this power uses the fact that you have here 1/2 of the action of the instanton. The instanton has 8 pi squared in SU2. Okay, this is a 1/2 of the instanton. Okay, so it's a different power, and you can see that this thing is working pretty well with data taken by measuring and at the same time, but it works up to a certain level. At some stage, when the size becomes large enough, it's impossible to see anything. Everything becomes just very, I mean, the instantons are not, even these ones are not dilute. They come one on top of the other. And it's also, the fluctuations are so high, it's hard to see anything. But of course, you can do something, because you can always look at that, what happens on the lattice, because on the lattice you can compute non-perturbative things. And what do you expect? You expect that when the torus is very large, compared to what? With lambda QCD, because the size, what matters is really lambda QCD, which fixes the scale of Yang-Mills theory, okay? When the size of the torus becomes large enough, then it would be irrelevant that you put magnetic flux or that you have infinite, that the torus, I mean, what boundary conditions you use or not, that doesn't matter. You should just approach an energy which grows linearly with L, as confinement tells you, with a coefficient, which is the string tension, which should coincide no matter what boundary conditions you get. What is the value of this sigma that people measured in periodic boundary conditions, whatever? 5. And this is what we get actually by measuring. So these lines here are semi-classical calculations, and these points here are measurements. And you see that up to here, beyond this point, it's hard to do a semi-classical calculation, but beyond the curves extend very smoothly, and at some stage recover even rotational invariance, because these two lines here come from different loops, which are oriented differently with respect to the magnetic field. Okay, so it's very similar to adiabatic continuity, and we don't see a phase transition. We don't even see a crossover. We don't see any big change. And actually, the semi-classical data is actually pointing in the good direction. This one that started 0 grows. This one that started high decreases to become close. Okay, so let me give you my summary and conclusions. Okay, first, concerning these mathematical questions I was asking at the beginning, something that I would like to say. Well, in quantum field theory or in statistical mechanics, when the space that you're interested in is Rn, boundary conditions don't matter, especially in systems that have a gap. I mean, there is a correlation length. Much beyond that, there are, of course, exceptions. Maybe there are coexistent phases or anything like that. But in general, it doesn't really matter what the boundary conditions are when the system is very large. However, boundary conditions and topology are very important. Why? We saw the examples. They are a fantastic tool to identify the local structures that do play a crucial role in the dynamics. But their existence does not depend, it's a local solution. So it does not depend on the boundary conditions you use. Only the number, for example, in the case of kinks or in the case of vortices, does depend on that, but not their existence, okay? So, and also answering the other, what matters is really the free energy, which is actually dressed up. So it's not just the classical, it's the dressed up. Okay, more specific conclusions and summary about fractional instantons. In four-dimensional Yang-Mills theory, there are classical solutions, which are self-dual, made of lumps carrying fractional topological charge. They exist irrespective of topology. Their action scales like 1/n, surviving the large n limit. A collection of m of these objects has as the number of degrees of freedom equal to 4m, because they're just the position that matters. These objects behave just like a gas of objects in 4 dimensions, a gas or a liquid, doesn't matter, okay, 4m. Okay, you can also have ordinary instantons, but because of the same reason as before, because of entropy, this only happens when some of them come together at the same center. So this is normally suppressed, okay? Computing the Wilson loop around these instantons, you can verify, or you can calculate, in the case you have exact solutions, the total flux around is of an element of the center, e to the 2 pi n over n, okay? So they have chromoelectric flux, even very far away, okay, when you have these vortices. Computing the expectation value of large Wilson loops on an ensemble of these objects, we have verified that they actually do give rise to area law with a string tension that is related to density. And actually there is a quantity you can form, which is a combination of topological susceptibility and string tension, which is dimensionless. And this number seems to be constant. So it's important to test that there is a relation between two things which might have the same origin, these fractional instantons. And well, of course, here I didn't say much about the deconfinement phase transition, but it is in this image, it's related to a kind of percolation. Let's see. Well, one instanton cannot exist isolated.
You're completely out of time, right? So maybe.
Yeah, can you give me 2 minutes? Yes. This thing does not exist isolated, but you can make arrays of 1, 2, 3 dimensions, and furthermore, and okay, and they are also this welcome not only as a possible explanation of confinement, but also because they explain the dependence on the theta parameter, the possible connection to renormalon as Mithad explained, the behavior of Jamil's fields close to TC. So the main difficulty is, of course, is to validate the semi-classical ideas in the case of strongly coupled dynamics. That, of course, I have nothing to say, that I would just tie to what the talk that Unsal was giving to us. There are new ideas on the line of thimbles and things like that, that if they are successful, they will possibly give a rationale to explaining this semi-classical interpretation of this within the QCD dynamics. And well, nothing else. I don't have too much to say. I just let me put that transparency to finish, and I will answer questions.
All right. Yeah. Thank you very much for this fascinating talk. So I already see a hand raised by Mithad, but maybe before we give the word to Mithad, let's see if there's questions from the young people in the audience also. Okay, then I don't see any right now, so then let's have Mithad ask the question.
Okay, if young people comes, they can take from me. So can you go 3-4 transparencies earlier? Slides earlier?
Here? Okay. Where?
No, one more. 2 more actually. This one. This is very nice. Go forward. The fractional instanton result. Fractional instanton result.
Before, you mean?
One more. No, this L to the 8 divided by 3.
Okay. That one more here. This one. Yeah, sure.
One more, please. Yes, this page. Okay. Either this page or previous page. So here, indeed, on small t 3 times r, so there are these fractional instantons, but and indeed, if you take ensemble of them, they generate these very interesting effects. But I just want to clarify one thing. I am completely convinced with you that there is a numerical solution for this fractional instanton with topological charge 1/2 and action 1/2 compared to instanton. But we do not yet know an analytic solution for that configuration, do we?
Well, that was what I was going to say at the end, but I just stopped that. I'm working on that because I told you before that I did something like that in the case of the vortices. I have a method to construct the solutions analytically in a power series. So actually the same thing happens in the case of these instantons that with respect to the vortices, that there is, in this case, of course, not an area, critical area, but actually a critical proportion of the totals in which there is a solution, which is known analytically, actually was found by Toft, which is very dull. It's just constant field. Okay.
Yeah, it's very boring.
Yeah, exactly. And only exists for these fixed proportions. However, I have developed a method to obtain solutions deforming away from this. So I have a way, for example, I can write a formula, I can write a picture that if you move away from this situation, you get something that has a lump, it has a size, everything like that. And there are many parameters in the game because you have n, you have the sizes, and I have sort of the hope that in some limits, this becomes easy. For example, in the Larsen limit, or when the coloring geometry, and actually having this analytic formula is very useful because you can do, for example, zero modes. You can do many things. You can do the NAM transform. I mean, actually, I've done it in SU2. So this would be my aim. That's what I'm working on now. So in principle, that's not yet finished. Yeah, go ahead.
I just want to be, more quickly. So you made a remark about Polyakov model saying that there is a confining flux tube between monopoles. I think monopoles are just screened there, right? So they just, if you insert a test monopole to the Polyakov models, right, to the Euclidean vacuum of the Polyakov model, it is just screened. There is no flux tube there for the monopole.
What situation are you talking about?
Just few slides earlier. I just took a note, but I didn't make it. Yeah, this page, the last remark. Next page.
Next or before? No, before. Here?
No.
Oh, no, confinement, no? Okay, sure.
This one?
Yeah.
No. Gosh, okay. Maybe we can chat privately, maybe.
Okay.
But I
think we have a
I agree with...
I think you mean this one, I guess. Gauge theories in 3 dimensions with monopoles also confined. But then in 4,
okay, this one. You say gauge theories in 3D with monopoles also confined because it takes one. Okay.
Yeah, and you know that.
That's. I think monopoles in that ensemble, just by Debye mechanism, they screen. The thing that forms a flux tube is really electric charge.
Well, I'm talking about 3-dimensional theory, and this can be proven, say, for U1 monopoles. I mean, the theory.
This is not important. So
okay,
I just want to make one last remark. So your characterization of this codimension, 4 objects being instanton codimension, 3 being monopoles, etc. I totally agree in 4 dimensions, but I think you should really consider in dimension D, codimension D is instanton. In that case, we see that, for example, in 3 dimension, the monopole is instanton in 3 dimension, but it's a particle in 4 dimension.
That's exactly what I was saying. That's exactly what I was saying.
Okay, very good. So
it's precisely that. Yeah.
I think we have to cut the discussion here.
Okay, very good. Sorry.
Time slot, including
I'm sorry.
We can take this for later. So I would say for now, let's thank Antonio again for this nice talk.